Hello, this is Mr. Best. Welcome to Chapter 7, Homework Questions. We're going to be working on 7 through 13 in this video. Question 7. A grocery store is offering a sale on bread and soup. Khalil buys 4 cans of soup and 3 loaves of bread for $11.67. Rhonda buys 8 cans of soup and 1 loaf of bread for $12.89. Write equations for Khalil's and Rhonda's purchases. Well, what are the things that we don't know? We know how many they're buying of soup and loaves of bread, but we don't know the cost of each of those. So let's make that our let statement. So for part A, even though these are not the equations just yet, we need to write let statements. So let, I don't want to use S, let's use C. Let C equal the cost of a can of soup. And then for the other one, we will let B equal the cost for a loaf of bread. Now, to write our equations, we want to look at the 2 different purchases. The first one being Khalil. He bought 4 cans, so 4 times the number of cans, or 4 times the cost of each can, plus 3 loaves, so 3 times the cost of each loaf is equal to $11.67. And then we have Rhonda at the same place, bought 8 cans of soup and 1 loaf of bread for a total of $12.89. And so those are the 2 equations. That's part A. Part B is going to want us to solve the system to find the price of 1 can of soup and the price of 1 loaf of bread. So I would say, in terms of which method we want to use, either choice substitution or elimination would be fine on this one, because you do have a variable that you could solve for very easily in the B in the second equation in Rhonda's, because the coefficient's 1, but it is set up for elimination where the variables are already on one side and the constants are on the right side. But to solve this, we are going to have to multiply at least one of the equations by a number. I'm going to go ahead and multiply Rhonda's equation by -3 so I can get my b's to cancel. So this would be -24c minus 3b is equal to 38.67. And that would be negative. And then I'm just going to rewrite the second equation down. Rewrite the first equation. And then add those 2 up. So that'll be -20c, the b's cancel, is equal to -$27. Divide by -20. And we get the cost of a can of soup for $1.35. And we still need to find the price of a loaf of bread. So we'll plug that back into one of the equations. I'll plug it back into the first one. So 4 times $1.35 for a can of soup plus 3 loaves of bread is $11.67. So 5.40 plus 3b equals 11.67. Subtract 3b will be equal to 6.27. Divide by 3. And we get $2.09. So let's go make sure we answer the question for B. It does find the price. Right now I just have solved the system, so we want to make sure that we answer the question. And when you write the answer, make sure you indicate what the label is. In this case it's dollars, so use the dollar symbol. Question 8. If 2 expressions are equivalent, they can form an equation that is considered to be always true. For example, since 3 times the quantity x minus 5 is equivalent to 3x minus 15, then the equation, when you set those two equal to each other, is always true. That is true for any value of x. If two expressions are equal only for certain values of the variable, they can form an equation that is considered to be sometimes true. For example, x plus 2 is equal to 3x minus 8 only when x equals 5. So the equation, when those two are set equal to each other, is said to be sometimes true. If two expressions are not equal for any value of the variable, they can form an equation that is considered to be never true. For example, x minus 5 is not equal to x plus 1 for any value of x. So the equation, x minus 5 equals x plus 1, is said to be never true. So there's really three different scenarios that you can have when you're solving an equation. You have always true, which we usually say for something like this, that the solution is all real numbers. All right. For something like the second one, when it's sometimes true, you get a specific value or values. And then the last one, we would get something when we went and solved where the variable canceled and we were left with a untrue statement, so we would say that there are no solutions. Okay, and then on the top, I guess, the variables also cancel, but you're left with a true statement, so that's the difference between the first and the last. Now the question is the equation always, sometimes, or never true, and justify your reason completely? So we're really just solving this, but we're explaining our answer at the end. So x plus 3 squared is x plus 3 times x plus 3. So we will use our generic rectangle or our distributive property. I'm going to go ahead and just distribute. X times x is x squared. X times 3 is 3x. Then we have another 3x and a plus 9. And so I'm going to go ahead and combine x squared plus 6x plus 9 equals x squared plus 9. We've had problems like this where we have to subtract the x squared, and in this case, as the other ones, the x squared cancels for right now because we haven't got to the part where we're solving quadratics just yet. And now we can solve for x. So we subtract 9. We get 6x is equal to 0. We divide by 6. And x is equal to 0. So is it always, sometimes, or never true? Well, it's sometimes true. And the only time it'll actually be true is when x is equal to 0. And we justify that by showing our steps in terms of solving. Consider the sequence that begins 40, 20, 10, 5. Based on the information given, can this sequence be arithmetic or can it be a geometric, and why? So when we're looking at the sequence, we have, once again, 40, 20, 10, and 5. And how are we getting from one term to the next? If it's arithmetic, you're adding. If it's geometric, you're multiplying. So you can see we're dividing by 2, but we want to use multiplication. So we're multiplying by 1/2. So it is going to be a geometric sequence. All right, and make sure that you write the y down also because it is being multiplied. On part B, assume this is a geometric sequence, so if it continues, the pattern continues getting multiplied by half. On graph paper, plot the sequence on a graph up to n equals 6. So yours is going to look a little bit better because it's on graph paper, but I can kind of show you what this will look like. Once again, we're going up to n equals 6. Right now it's up to n equals 5, so if we continue this, half of 5 is 2.5. Half of 2.5 is 1.25. And so that gives us 6 terms. So there's the graph. Your x-axis I put as n, and the y-axis I put as t, and because it is a sequence that we're looking at here. And I didn't connect the points because it's discrete, because we're talking about individual terms. So we have term 1, 2, 3, 4, 5, and 6. And then those values would be your dependent variable. All right, part C. Will the values of the sequence ever become 0 or negative? Explain. Well, as we continue on, we keep taking 1/2 or multiplying by 1/2. So we keep cutting it in half basically every single time. So these numbers are going to get small, but will they ever become 0 or negative? Well, if you keep cutting something in half, there's always going to be something left. As small as it is, there's still a little bit left at each time. So even if we kind of continue over time, the value will never become 0, and it'll never become negative, because once again, you're only taking half of a positive number, which would never give you a negative or 0. So I said no, it'll never be 0 negative, because half of a positive number will still be positive. So once again, it'll never be 0 or negative. It gets closer and closer and closer to 0, but theoretically it'll never become 0. Question 10. If a ball is dropped from 160 centimeters and rebounds to 120 centimeters on the first bounce, how high will the ball be? And 3 questions: on the second bounce, on the fifth bounce, and on the nth bounce. So we could set this up as potentially a table, and then maybe as an equation, because on the nth bounce we need to know for any bounce. So if the ball is dropped from 160, so let's kind of create a table here. And on 0 bounces, it's at 160 centimeters, and it rebounds to 120 centimeters on the first bounce. So the next bounce, the first bounce, it's being dropped from 120 centimeters. And then so on as we go along here. So what's happening? Well, 160 goes down to 120. But when a ball is being dropped, we did this in class, is that it's not being dropped at a linear rate. So 160 to 120, you're not just going to subtract 40 again and get 80. You got to figure out what that multiplier is. So to do that, we can work backwards. Normally, we're asking ourselves, 160 times what is 120? But that's not a number that we, can necessarily think off the top of our head. 160 times what number is 120? So what we can do is we can just take 120 and divide by 160, and we'll get a value of 0.75. So the multiplier is 0.75. So to find the next height of our bounce, we can multiply 120 by 0.75. And on bounce 2, it's going to drop from a height of 90 centimeters. So on the second bounce, it's at 90 centimeters. We can continue this 3, 4, 5 out to the fifth bounce to figure out what that one is, and then the last one we'll set up an equation so we could really figure out any bounce. And so I brought my table all the way out to the fifth bounce, and it goes to 37.96875, but we will round that to approximately 37.97 centimeters by the fifth bounce. So to answer part C, this is a geometric sequence. We have our multiplier. We know that the height is being multiplied by 0.75, which makes sense because the height is going down, it's decreasing, so that multiplier should be between 0 and 1. And then we also have the initial, which is the top one. At 0 bounce, it's 160. So for the nth bounce, we would say that T of n is equal to the initial height, which is 160, and then what's happening to that 160? The 160 just keeps getting multiplied by 0.75 over and over and over again. So when something is being multiplied over and over again, you're going to raise it to the power of whatever bounce that is. So if I wanted to know what the 10th bounce is, I could just plug it in. Now, that is part C, but just to verify part B, we could say T of 5 is equal to 160 times 0.75, and plug 5 into your calculator and see what value you get. And if you do that, you'll get 37.96875, which is the same value we got before, and we just rounded it. Question 11. Data for a study of a vitamin supplement that claims to shorten the length of a common cold is shown below. So you have the number of months taken the supplement and the number of days the cold lasted. And we had looked at this problem previously as well. You previously created a linear model for this data by eyeballing it. Now create a model that is consistent with your classmates by finding the LSRL. Sketch the graph and the LSRL. So on this one, you will need your graphing calculator. And if you enter in the data and calculate the LSRL, you'll get a value of y equals negative 1.581x plus 5.372. And then also sketch the graph. Is a linear model appropriate? Provide evidence. So when you look at the residual plot, there is no apparent pattern. So therefore, yes, the linear model is appropriate. All right. Part C, find R and interpret R squared in context. So once again, when you calculated the LSRL, make sure your diagnostics is on, and you would find R, which is your correlation coefficient, is equal to negative 0.952, and then R squared is equal to 0.907, or what we're more concerned about is the percent, so we'll change that to 90.7%. And so remember, when you are interpreting the R squared, we're looking at the variability. And so the statement 90.7% of the variability in the length of the cold, which is your dependent variable, can be explained by a linear relationship with the amount of time taking supplements. And then we have the last question here, D. Describe the association. Make sure you describe the form and provide evidence of, or for the form. Provide numerical values for direction and strength and interpret them in context and describe any outliers. And so to answer question B, you got to go through and explain each part. And as you go through and look, the first part is talking about the form, so the relationship is linear. The next sentence talks about direction, where it's negative, and not just saying it's negative, but explaining what the negative means. And then the association is the strength. It is strong, and talks about the variability. I didn't write the sentence out again because it's in part C. And then the last one is the outliers. Do we have any outliers? So form, direction, strength, and then outliers. Question 12. Simplify or multiply each of the following expressions. On part A, we are dealing with one term being multiplied by itself twice. So I'm going to go ahead and expand it out. And you can see both of them being multiplied. I'm even going to take it a step further and expand each individual term out. So it's going to be the same, but I want you to see how all of this plays out if you haven't figured out, or maybe you're still struggling with what do you do with all this stuff. So if I expand it completely out, and you should be doing this anyways if we're not getting these right and we haven't quite figured out yet. You got 3 times 3 is 9. So in the original problem, that means the 3 was being squared. You have x times x times x times x, which is x to the 4th. So once again, in the original problem, you had x squared being squared. And then you have y times y, which is y squared. And going back to the original, the y was being squared. And then the z, you have z to the 4th, and then another z to the 4th, which would be z to the 8th. And so once again, in the original, that's z to the 4th squared. So if you're using your properties of exponents in the beginning, you have 9. You multiply the exponents because you have a power to a power. And that's where you get the answers a little quicker. But by expanding them out, we see exactly what's happening. On part B, same idea. You have r squared times s divided by r s cubed times t. And I'm going to do the same thing. I'm going to expand the whole thing out 3 times. And then on this one, I'm not going to expand it completely out like I did with the A, but you can see hopefully everything that's happening here. So on top, you have r squared, and r squared. So that would give you a total of 6 r's. Now, on this one, we're multiplying the top, but that means you add the exponents, where on part A from the original, you had an exponent raised to another exponent. That was the difference there. That's why you were multiplying up here on A, and then down here we're adding the exponents. And then you have 3 s's, so that's s cubed. And then on the bottom we have r times r times r, so that's r to the third. And then s to the third, s to the third, s to the third, that's s to the ninth. There's 9 of them. And then t to the third. So we've simplified the 3 into 1, but we still have r's and s's in the numerator and the denominator, so we need to simplify those. If we wanted to at this point, now that we've simplified a little bit, we could expand out. And you'll see what this property of division is. And 9 s's. I think that's 9. 3 t's. So with division, factors cancel. Everything's being multiplied. So we can cancel 1, 2, 3 r's. But that leaves us with 3 in the numerator. And then on the s's, we can cancel 1, 2, 3. That leaves 6 s's in the denominator. And then none of the t's cancel. So that's still there. So it looks like we're left with r to the third divided by s to the sixth, and then t to the third. So once again, it might take a little bit longer to expand out, but you can literally see everything happening. It makes it a little bit easier to make sure we get the right answer. You might recognize that you will take the exponents in division and subtract them. 6 minus 3 is 3. Yeah, you can either do 9 minus 3 and get the 6 on the bottom, or if you do 3 minus 9, you'll get negative 6. But then remember, negative 6 is exponents we have to simplify. And then the t to the 3 is just on the bottom there. Part C. Part C, we're getting away from exponents a little bit here, and we're multiplying binomials. Binomial is 2 terms, 3m plus 7 and 2m minus 1. And we can use our generic rectangle or the distributive property. So we have 3m plus 7 and 2m minus 1. Don't forget about the minus 1. So it looks like we will get 6m squared minus 3m plus 14m minus 7. Combine your like terms, and you get 6m squared plus 11m minus 7. If you're using the generic rectangle, you'll see the same 4 terms. And then you combine them as well. And then D. D is the same, but you have to recognize that if you are squaring a binomial, you have to expand it out. So you still have a length of a generic rectangle times a width. So this will leave you with x squared minus 3x plus 9, or x squared minus 6x plus 9. And as I said, you can still use the generic rectangle. It would be x minus 3 and x minus 3. Question 13. Write and solve an equation for the problem below. If 150 empty water bottles weigh 4.5 pounds, what would you expect 90 empty water bottles to weigh? So, a couple ways you could handle this. The first way I'm thinking is to find out how much one empty water bottle weighs. And we can do that by taking the total weight, 4.5 pounds, and dividing that by 150 empty water bottles. When we divide, we are going to get a value of 1 on the bottom, which is what we're trying to figure out how much one empty water bottle weighs. So if you take 4.5 and divide by 150, you will get 0.03 pounds. So that's how much one empty water bottle weighs. Well, now that I know what 1 weighs, we can figure out what we think 90 of them will weigh by multiplying. So we're going to take 90 empty water bottles multiplied by the weight of the 1 individual water bottle, and that should give us the weight of all 90 of them. And that would be 2.7 pounds. So we would expect 90 empty water bottles to weigh 2.7 pounds for 90 empty water bottles. And always make sure you answer the question. To show you an alternative way maybe to look at this is we could set up what we call a ratio and a proportion, similar to what I did on the top, but instead of doing the 4.5 and dividing by the 150 and figuring that out individually, we could say we don't know how many pounds 90 water bottles weigh. So we could set it up like this and then multiply and solve that equation that way too. So either way is fine.